Today's video is on section 5.6, intermediate forms and L'Hopital's rule. So we're going to talk about recognizing limits that produce intermediate forms and applying L'Hopital's rule to evaluate them. So you've seen some intermediate forms before in the past, and we're going to review how to deal with those. And then we're going to talk about the ones where you can't use what you've learned before and how L'Hopital's rule helps us. So for instance, the limit as x approaches -1 of 2x squared minus 2 over x plus 1 is of the form 0, 0 because the limit of the numerator as x approaches -1 is 0 and the limit of the denominator as x approaches -1 is 0, but that is not the limit of that quotient in general. So we can do some manipulation here. So if I take the limit as x approaches -1 and factor that numerator, I see that then I have a difference of squares, so then I can continue to factor it. And I get 2 times x minus 1 times x plus 1, and then the x plus 1's on the denominator will cancel. And then I can go ahead and plug in that -1 because it won't make a undefined value. And I get 2 times -2, or I find that the limit is -4. And so the technique there was to factor and simplify. Okay, so sometimes it's easy as that. Next example is the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. And we see that both the limit of the numerator and the denominator are infinity. So I get my intermediate form of infinity over infinity. For this one, we're going to do some different manipulation. We're going to multiply the top and the bottom by 1 over x squared. And how that helps us is that now I have the limit as x approaches infinity of 3 minus 1 over x squared over 2 plus 1 over x squared. And that's helpful because when I take the limit as x approaches infinity, both this term here goes to 0 and this other term in the denominator of 1 over x squared go to 0. Circling a term like that and using an arrow and showing it goes to 0 or infinity or a specific value is official notation. So you are allowed to do that to show your work, just to let you know. All right, so then if both of those go to 0, I find that my limit is just 3 over 2. So our technique here was just algebraic manipulation. All right, our next example is the limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. And here if I notice, the numerator is also a difference of squares because I can rewrite that e to the 2x as e to the x squared. And then I get that the limit as x approaches 0 of e to the x minus 1 over e to the x plus 1 over e to the x minus 1. Those cancel. So I just have the limit as x approaches 0 of e to the x plus 1. So then I'm just going to get 1 plus 1, which is 2. Okay, so once again here, I used exponent rules and factored and divide or simplify. Okay, so just some algebra stuff. All right. Now, what if I change that last example where the denominator is x? So if you printed the notes or are looking at the notes I typed up, there is a typo. So that denominator should just be x. So if we look at the limit as x approaches 0 of e to the 2x minus x, I might think, maybe I can rewrite it as the limit as x approaches 0 of e to the 2x over x minus 1 over x. But once again, as that goes to 0, I'm going to get infinity minus infinity. Not super helpful. All right, so this is where L'Hopital's rule can be helpful. So what L'Hopital's rule says, it has all these words, but it basically says if I have two functions that are differentiable on an interval containing my point that x is approaching, okay, so x is approaching c, they don't have to necessarily be continuous at that point, okay, or differentiable at that point, but they do need to be differentiable over the interval. All right, so we're assuming that the denominator isn't equal to 0. So the limit of the fraction of f of x over g of x, if it's one of those intermediate forms, then is going to be equal to the limit as x approaches f prime of x over f prime or over g prime of x. So notice this isn't the quotient rule. I'm not taking the derivative of f of x over g of x. I'm taking the derivative of f of x and separately the derivative of g of x, and now looking at that new limit, okay? And so when I'm allowed to do this is when the quotient of f over g is 0 over 0 or plus or minus infinity over plus or minus infinity, okay? So those are the times I'm allowed to use this rule, and here is the rule. So I'm going to go over 7 examples of using this. You are welcome to try them on your own before I do each one. Pause, try, see what you get. You are also welcome to skip them if they look too easy, but I do recommend watching all of them at some point. Okay, here we go. First example. Oops, did not mean to pull that up. First example is of the intermediate form 0 over 0. So this was the one I was just doing. So I had e to the 2x minus 1 over x, and if I plug in 0, I get 0 over 0, which doesn't work. And we saw that we tried some manipulation, and that didn't work either. So what I'm going to do is I see that I have 0 over 0, and this is how we show our work for L'Hopital's rule. So by putting in parentheses one of those intermediate forms, this shows my next step uses L'Hopital's rule. Okay, so now I can take the limit as x approaches 0 and take the derivative of e to the 2x minus 1, which is going to be 2 e to the 2x minus 0, and then take the derivative of the denominator, which is just 1. And so now when I take the limit as x approaches 0 of 2 times e to the 2x, I see that I am just going to get 2, because I get 2 times 1. So there we go. So my original limit is going to equal 2. Next, intermediate form of infinity over infinity. So the limit as x approaches infinity of the natural log of x is infinity, and the limit as x approaches infinity of x is infinity. So I have that. So that shows my next step is L'Hopital's rule. So I take the derivative of the numerator, which is 1 over x, and the derivative of the denominator, which is 1. Simplify. I have the limit as x approaches infinity of 1 over x, which is 0. Fantastic. These are going well. Next, 3, applying L'Hopital's rule more than once. And so when I look at this, the indicator that tells me I may apply L'Hopital's rule more than once is that the numerator has an x squared in it, and the denominator is going to be one of those infinite cycles, right? Because I have e to the x or e to the negative x, so I can continually take a derivative without ever simplifying it, but the numerator will, just not the first time. All right, so right now we have, so if we go to negative infinity, right? So we're taking the limit as x goes to negative infinity. Right now I have a positive infinity over a positive infinity. So let's take our derivative. So limit as x approaches negative infinity of 2x over negative e to the negative x. So now if I plug in negative infinity, I'm going to get negative infinity over negative infinity. So I'm going to take the derivatives once more. So now I have the limit as x approaches negative infinity of 2 over e to the negative x. So when I look at that, I see that I have negative infinity. Oops, I forgot the negative on that. So now I have 2 over negative infinity, right? Or, oh my gosh, I'm sorry. 2 over e to the negative infinity, which is 2 over e to the infinity, which is 2 over infinity, which, remember, as the denominator gets larger and larger and the numerator stays constant, goes to 0. Next. So this one is a little different. Now we have something where if we look at the limit as x approaches infinity of e to the negative x times the square root of x, I get 0 times infinity, which isn't of the quotient form, but if I rewrite it, I can rewrite it so that it's a quotient that then allows me to use L'Hopital's rule. So what I'm going to do is I'm going to rewrite this as x approaches infinity and leave the square root on the top and move e to the x on the bottom so that it's no longer e to the negative x. And now I can say, oh hey, now I have infinity over infinity, which is one of the intermediate forms that allows me to use L'Hopital's rule. So then I'm going to take my derivatives. So I have the limit as x approaches infinity of 1/2 x to the negative 1/2, so square root of x on the denominator, and then my denominator stays as e to the x. Simplify this so I don't have a fraction over a fraction because that's always gross. So my numerator is 1, and then I get 2 square root of x e to the x on the denominator. And if I look at this as x goes to infinity, my denominator then is going to infinity. So then I get 0. Fantastic. All right, next example. Here we look at this and we have the limit as x approaches infinity of 1 plus 1 over x to the x. And if you look at this, you're probably thinking, oh, this looks like something I'm supposed to recognize. Yeah, this looks a lot like e. So we're going to prove that this limit equals e. So this is kind of a little bit of a longer example. All right, so let's take a look at it. So the first thing I'm going to do is I'm going to let y equal this whole limit. So y equals the limit as x approaches infinity of 1 plus 1 over x to the x. And so the reason I did that is so that I can do that logarithmic differentiation technique that we've talked about before. So I'm going to take the natural log of both sides, and how I know that I would do that is because I have an x in the exponent, right? And that's the easiest way, or the only way, to get that x out of an exponent, okay? So since we know that 1 plus 1 over x to the x, since this is continuous, we can swap the natural log and the limit. So we can put the limit on the inside or the limit on the outside and the natural log on the inside. So I'm going to rewrite this as the natural log of y equals the limit as x approaches infinity of the natural log, or that's continuous and natural log is continuous. Yeah, they both have to be continuous. Okay, so then I get the natural log of 1 plus 1 over x to the x. And now I can pull that x out in front of the natural log. So now I get the natural log of y equals the limit as x approaches infinity of x times natural log of 1 plus 1 over x. Okay, we hanging in there? All right, so then this isn't a quotient, so I can't use L'Hopital's rule yet, but I can rewrite it as a quotient just like we did in the last example. So now I have the limit as x approaches infinity. I'm going to leave the natural log of 1 plus 1 over x on the numerator, and then I'm going to write that x as 1 over x on the denominator. Okay, so now I can use L'Hopital's rule because I have 0 over 0, right? So if I plug in infinity, I get a denominator of 0, and then on the numerator I have 1 plus 0, and remember the natural log of 1 is 0. All right, so let's continue over here. So now we're taking the derivative. So, this will be fun. Yay! All right, so we do, for the first one, the natural log, so it's 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is negative 1 over x squared. And then my denominator is going to be the derivative of 1 over x, which is negative 1 over x squared. Okay, and we still have our limit in the front. Oh, forgot that part. So we're still taking the limit as x approaches infinity of this. Okay, and this, remember, still equals natural log of y. I don't need to take the derivative of that side because I used L'Hopital's rule. I didn't take the derivative of both sides. Okay. Oh my gosh. All right, so natural log of y equals the limit as x approaches infinity. Okay, let's simplify all of this grossness. Oh, well, this is pretty easy because this cancels with this. Fantastic. So now I just have the limit of 1 over 1 plus 1 over x, which now let's take a look at this. If I simplify that, I am looking as x approaches infinity, so this piece goes to 0, so I just get 1 over 1. So I have that the natural log of y equals 1. Oh, that's way easier. Put it in exponential form. Y is going to equal e to the 1. So I just figured out, thus, my favorite math word, that the limit as x approaches infinity of 1 plus 1 over x to the x, remember we set that equal to y, and we just found equals e. Oh, that's so exciting. What a great problem. All right, 2 more examples. Next one, intermediate form of 0 to the 0. So we have the limit as x approaches 0 from the right of the sine of x to the x. So we have x in the exponent. So this is where we're going to do that same process where we say let y equal the limit as x approaches 0 from the right of sine of x to the x. And the reason why we do that is because then when we take the natural log of both sides, we can bring that x out front. But first I'm going to switch the natural log and the sign, and we can do that because natural log is continuous. So natural log of y equals the limit as x approaches 0 from the right of the natural log of sine of x to the x. Now I'm going to bring that x out front, so natural log of y equals the limit as x approaches 0 from the right of x times the natural log of sine x. Whew. Okay. So now, this is not in fraction form, so I'm going to move that x to the denominator so we get a fraction. So I have the natural log of y equals the limit as x approaches 0 from the right of the natural log of sine x over 1 over x. Okay, so now we have a fraction, and if we look at that and see that when I take the limit as x approaches 0 from the right, I get the limit of sine of 0, or I'm sorry, sine of 1. No, sine of 0. Wait, sine. Sine of 0, which is negative infinity, yeah. Sorry. Little brain fart there. And then 1 over x, which is infinity. So here, that's okay. It's okay if we have our infinities don't have to match in terms of positive and negative. So now I can use L'Hopital's rule. So for L'Hopital's rule, now I have the natural log of y equals, and then I'm going to take the derivative of both the numerator and the denominator. So for the numerator, natural log of sine, so I have 1 over sine of x times the derivative of sine, so cosine. And then the derivative of 1 over x is negative 1 over x squared. So if I look at this, my numerator really is cosine over sine, so that's cotangent. So I have the limit as x approaches 0 from the right of cotangent of x. And I can rewrite that denominator as, in the numerator, as negative x squared cotangent of x. Okay. But I still run into a problem because I have, right now, I have infinity times 0, which is not super helpful. But if I move that 0 to the denominator, right, 0 on the denominator, then might get infinity over infinity. So let's rewrite this as using our trig identities. So I get negative x squared is going to stay on the numerator, and I'm going to write it as tangent of x on the denominator. And now I can see that I will get 0 over 0. Oh, sorry, I wrote that backwards in the previous one. It should be 0 times infinity. Okay, so now I have 0 over 0, which is an intermediate form where I'm allowed to use L'Hopital's rule. So natural log of y equals the limit as x approaches 0 from the right, and take the derivative of each of those. So negative 2x over, and then the derivative of tangent is secant squared. Fantastic. And so now if I look at this, I have secant squared. You can graph that if you want to. Convince yourself. Let's see here. Secant squared, if you want to think about it, you can think about it as 1 over cosine squared, right? And so thinking about as cosine approaches 0, I get 0. So then I get that the natural log of y is going to approach 0 there. So then I get, put that in exponential form. E to the 0 equals y. And so then I get, let's see here. So e to the 0 equals y, which it means y equals 1. So then I get that this whole original limit as x approaches 0 from the right of sine of x to the x equals 1. Phew. Okay, that's a long one. Very, very exciting. Okay, our last example is a little quicker. Here we have a limit as x approaches 1 from the right of 1 over the natural log of x plus 1 over x minus 1. And if I look at this right now, I have infinity minus infinity, which is not super helpful. But if I just basically go through and combine my fractions, I am going to get that I have, let's see here, so first fraction multiplied by x minus 1 minus second fraction multiplied by natural log of x. Okay, so now if I look at this on its own and I plug in a 1, then I'm going to get 0 over 0, which then allows me to use good old L'Hopital's rule. So now if I plug in L'Hopital's rule, I'm going to get that I have 1 minus 1 over x is the derivative of the numerator. And the derivative of the denominator, we have to use our good old friend product rule. So I have the derivative of, let's see here. Did I do this correctly? Oh, yeah. All right, sorry. I was looking at my notes. So the derivative of natural log of x is 1 over x times x minus 1 plus the derivative of, and then I leave the first one alone and take the derivative of the second one, which is just 1. So here, I'm going to do some manipulation because I have fractions within fractions, which is just gross. That's nasty. So I'm going to multiply the top and the bottom by x over x. And so then I'm going to get x minus 1 on the numerator times x minus 1 on the denominator plus x natural log of x on the denominator there after I multiply everything. Still can't quite take that limit yet because I currently get 0 over 0. So we're going to do L'Hopital's rule one more time. And then I'm going to get the limit as x approaches 1 from the right-hand side is going to be 1 over 1 plus natural log of x plus, and then we have to do a little bit of product rule over here, right? So natural log of x times 1 plus x times 1 over x. Now I can take that limit, and so I get a 1 on the numerator, and then I'm going to get 2 on the denominator, so a half. Yay! Okay, those are all the examples I have for you today. Sorry this video was lots of examples, but hopefully you'll find